Suppose that x and y are topological spaces and f is a function from x to y. F is continuous whenever the pullback of an open set in y is again open in x, or analogously pullback of a closed set in y is again going to be closed in x. Now we will introduce another concept. A function is going to be called an open function provided it takes open sets of x onto open sets in y. That is, if V is an open set in x, and if you know that f of V is again open in y, so it takes every open sets to open sets in y, such a function is called an open function. Very similarly, one can define closed functions also. If f is a function which takes closed sets in x to closed sets in y, we call that such a function as a closed function. There are similarities as well as differences with openness and closeness as well as with respect to the continuity also. Some features are very similar to the continuity of the functions, but there are enough differences too. In fact, the openness of a function or closeness of the function guarantees the f inverse continuity whenever f inverse exists as a function. That is, once you are having a bijection, then obviously this openness is a necessary and sufficient condition for the inverse function f inverse is going to be continuous. That actually says about that, openness or closeness, whatever you are trying to look at. Let us just quickly look at the facts, how the differences are basically from the continuity of this continuity notion and all. Suppose that see, first there are some similarities are there, but obviously the differences we will discuss first. First of all, look at the definition. Definition says that f is a function from a topological space x to y. It is said to be an open function provided every open set v in x, f of v is again open in y. That is how open function is defined. Very similar way, closeness, as I mentioned before. See, suppose we have the inclusion map. Inclusion maps are continuous, that we know. So what happens in the case of openness of a function? Just look at a topological space x and a y be a subspace of x. Then look at the inclusion map, which takes y to x. That is, each y in y is mapped onto y itself. That is how inclusion maps are defined. Then inclusion map C, y is sitting inside x. Whenever y is a subspace of x, y is always open in y. So inclusion map in general or need not be an open map at all, very clearly, because y is an open set in y, but I of y I mean the image of the entire y may not be open in x, not be closed also. So in general, you can't say that inclusion maps are neither open, they are open or closed, neither open nor closed. But it is, what is going to happen is an inclusion map from y to x is going to be open if and only if y is open in x. Very similarly, you can think about closedness. Inclusion map is closed if and only if y is closed in x. Because y is a subspace topology, you are going to have it, right? Naturally. Now that is one difference if you are looking at. Another important property or difference if you want to discuss is something like that. See, whenever you are looking at a function f from a topological space x to y and continuity is concerned, continuity never bothers about the codomain part, which I mean it looks only on the f of x part, f of x, the range part. How the range is, that is what is important. for the continuity. It never considered about the entire domain business, and sorry, entire codomain business. But it means it's really depend on what happens on f of x. But open maps are not like that. In the sense, see, for example, X is a topological space with the tau. Y is equipped with the U1 and U2, two topologies are there. Then you just look at U1 restricted to U1 with the f of x, I mean relative topology of f of x with respect to U1 as well as U1, U2 with respect to f of x. Then see, whenever you are talking about continuity of a function, both the topologies are really concerned. So f is, suppose U1 restricted to f of x, restricted I mean U1, the subspace topology on f of x, that is U1 is concerned and U2 f of x is concerned. If they are agreeing, the open sets are agreeing, then f is continuous with respect to tau U1 is same as that of f is continuous with respect to tau U2. But that case is not going to hold in the openness. It is not going to be a truthful statement in this case. What I mean by that is, see, for example, you take an function f from R to R2. Both are Euclidean spaces with the usual topologies. And we will take the map x going to x0. So geometrically what happens is you have the domain part is the real line and codomain part is the plane with usual topology. So each x, it is marked on to correspondingly x0. This is how the map is going to, the function is going to behave. That is our f. Then with usual topologies of x and y, my capital X is R, capital Y is R2. See, this fellow is, see, if you are considering it's a function from R to R2 with usual topologies, then it is not going to be an open map, open function. If it's not going to be an open function, why is it so? See, for example, the entire domain R, X is open. But in R2, the image is going to be the x-axis. That is not going to be open in R2. But if you are taking or considering f from R, I mean x to R to R, I can say, R to the real axis. So if I'm not considering R2 here, instead of that, if I'm just looking at the relative topology on the real axis, then f is going to be an open map. So very similarly, you can think about the restrictions, and the restriction of an open function need not be an open element. All these kind of arguments you can make use of in the case of closedness also. I mean closed functions also. So there are basic differences from the continuity concepts and all. So we will see more properties while looking along with this line. Now let us see, we have an important class of functions which are projection functions. So what about projection functions? See, if you are having x1, x2, etc., xn, n topological spaces with the corresponding tau i's, and we have the product, I may call it as x, topological product with the product topology, and pi i's, they are the projections, the ith coordinates. They are going to be open, obviously, because see, it's almost clear. See, one can do it as an exercise that see, whenever you are trying to look at a function is open, it is enough if you are looking at what happens on the base. All the base elements are going to be taken to open subsets in the codomain. It definitely gives you that the function is going to be an open function. So just look at the base element for the product topology here. All the base elements, you can easily see that clearly going to be taken to an open subset of the coordinate spaces, which says that projection functions are open. So we will think that they are closed also, but it is not. In general, a projection functions are not going to be closed. How to see that? Just with an example we will do. Again, take the plane. I'll consider R2. So on R2, just look at the first projection, that is pi1 of a point xy. I will just mark it as x for every xy in R2. So every point mapped onto xy, just push it to the x coordinate. That's all. That is how it is defined. Now this map, this function, it's actually a map because it's a continuous function. Projections are continuous functions. They are open functions. So they are open maps. It is not going to be closed. How to see that? To see that, just look at a particular subset. For example, H I may call, or A I may call. This consists of all the points in the xy in R2 such that xy equals 1. Xy equals 1 means basically it is a y equals 1 by x kind of things. That is, xy is going to be 1 is the rectangular hyperbola you will get, right? That is what is xy equals 1. So what happens for this? This is my A. A is going to be a closed set because its complement is going to be an open set in R2. Clear? Because outside A, if you are looking at any point, you can find a neighborhood which is sitting entirely in that complement part. So the complement part of this A is going to be open, which says that A is closed. Look at the projection, first projection, this coordinate projection I mean. If you are projecting, what you are going to get? You will get the entire line except 0. So you will be getting R minus 0. That is what the image of A under the pi1 map. Pi1 of A is going to be this fellow, R minus 0. What about R minus 0? With usual topology, it is not going to be a closed set, right? All non-zero real numbers, if you are looking at it, it's not going to be a closed set, right? So a closed set need not be mapped onto a closed set here. So it's not going to be a projection is not going to be a closed function always. There are situations where when it's a very nice question that when these projections are going to be a closed function or a closed map. One can try it as a good exercise if you want. In general, they are not going to be closed, but they are continuous, I mean, as well as open. Now, let us introduce the most important concept, which is going to be the notion of equivalence in topological spaces. That is our next aim. See, in the category of topology, if you are looking at, our playing objects are just topological spaces. So X is some topology and Y is having some other topology. Y is a set with some topology. So when, see, from X to Y, how will you move means through a continuous function. That is our transitions, usually called the morphisms, the category of topologies. They are continuous functions. So how will you define the equivalent objects now? A topological space is looking like another one. That is, X is looking exactly or similar, looking exactly a copy like Y, or Y is looking like X. How will you say that? So as continuous functions are the carriers, obviously the equivalent concepts are something other than the bijective functions, which possess continuity, as well as the inversion is also going to be continuous. That is the basic concept of equivalence in the category of topology. So how will you define that? So we need X and Y are topological spaces, and if you have a function f from X to Y, which is going to be a bijection, and it is continuous, and inversion is also going to be continuous. Then what is going to happen is x and y are topologically equivalent. That is how we are going to define formally the equivalence, and we will say that it is by the terminology homeomorphisms. So what is a homeomorphism? We'll define very formally a space x and a space y. If we have a bijection 1, 1 and not 2, and if f is continuous and f inverse is also continuous, then we say that x is homeomorphic with y. So bijective, continuous as well as inverse and also continuous, such maps are going to be homeomorphism. In that case, homeomorphic images we are going to call. This is the concept for equivalence in the category of topology. So two topological spaces are looking alike whenever there exists a homeomorphism, which means a bijection. The onward journey as well as the backward journey are going to be continuous process. So they will carry all the topological properties well. That is what we are going to see next. So this is the fundamental notion of equivalence, what it happens here. Obviously, we can just make some more comments about homeomorphisms and all. See, whenever you are trying to look at homeomorphism, bijective correspondence you are looking at, and f is continuous and inverse function is continuous. So that is what is a homeomorphism, existence of a homeomorphism. So bijection, see, inversion is continuous, that is f inverse is continuous, as we have mentioned before, is equivalent with the notion that f is an open map. F is open, it actually gives that it takes open sets of x to open sets of y, which is going to be equivalent with the continuity of f inverse, says continuity of that fellow, because ideally what you look at the continuity of f inverse is nothing other than f inverse you have here. So f inverse I mean the pullback of f inverse with an open set here, you will go to f inverse of that fellow, but that is again going to be here, it is open, that is the openness is going to do, which means since you are working with the bijection. So this homeomorphism can be stated equally in many ways. Once you have a bijection and a continuous maps, and instead of saying that f inverse is continuous, one can say that f is an open map, right? Open map I mean open continuous bijection, that is equal with homeomorphism. Or just start with a bijection, simply say that f inverse is an open map, that also will do, right? F inverse is also an open map, I mean openness is given. In that case, what will happen? Openness of f inverse give its inverse, that is f is going to be, and it is a map, it's a continuous map. These are, so various ways are there to understand the equivalent concept. We will just state it precisely. As a proposition, we will write it. Here it says, all the four statements we have made it here. F is a function from x to y. X and y are topological spaces. Then what one says is simply the definition. I mean, you can use the definition, stick upon with the definition. F from x to y is going to be a homeomorphism. It means it's a bijective map. Onward journey is continuous. Inversion is also continuous. I mean, f inverse is also continuous. This is what it says. For 2 and 3 we have discussed already, because f inverse continuity is guaranteed by openness, right? So 1 and 2 are equivalent. In fact, 2 and 3 are also going to be equivalent, because f inverse is an open map. Once you are saying that, map gives continuity of f inverse, openness of f inverse, as I mentioned before, gives the continuity of f. So all the three statements are going to be equivalent. What about 4? A moment's thought will reveal that why it is equal with 4. Because see what it says actually, it's a theoretical play only, interplay only. Our function is from x to y. So it says something about one-oneness as well as on-to-ness, how to be guaranteed with in terms of identity functions. If we have the function f, see x and y are the topological spaces. See, whenever you have a function g, so that see f is the given function, remember that. If there exists a function g from y to x, then look at the composition g dot f. So g dot f will work from x to x, right? So what it says, g dot f is going to be the identity function on x. Such an g exists. Second part actually gives very similarly, you start with y to x or g is there, then x to y or f is working. So just look at our f dot g. If it is identity function on y, then what you are going to get is homeomorphism. Why they are going to be equal with other three statements? See, these two parts, what actually they are giving is, see, whenever you are saying that existence of g in such a way that g dot f is identity on x and g dot f is f dot g is identity on y, it ensures that the function is both 1 as well as 2. That is a theoretical uh, exercise. So it's going to be a bijection. F is continuous, G is also continuous, so it's going to be, obviously whenever such an identity function comes in the both cases together, F and G are inverses to each other. So it guarantees that F and G are continuous also. So bijection, that is what this diagram commutes, it says. Usually we say that whenever you are drawing in this way, it's a diagram commutes. So that is the last part, and it's also equivalent with the homeomorphisms. All these are various avatars of saying that if is a homeomorphism or topologically x and y are equivalent. So now we will just define what is more technical word, embedding or embedding. Formally, x and y are two topological spaces, x2 as well as yu. So as I mentioned before, homeomorphism actually gives topological equivalence. So embedding is nothing other than that you can just place x inside y as a homeomorphism. That is, you can get, if there exists a function e from x to y such that this e from x to y is a homeomorphism. If you want to talk about that, see, we are working from x to y. Now a copy of x is there, that is e of x in y. So this e of x part, if you are looking at, that makes onto-ness. Then the function e considered from x to e of x, it is going to be a onto function. Moreover, u is the topology on x, y is given here, it is to. So u restricted to u with the subspace topology. I mean, u is already there, so e of x with the subspace topology, u restricted to e of x. That's all. Natural topology, what is happening there. So with respect to that topology, this is an onto map, and that's becoming a homeomorphism. We'll say that f is an embedding, E is an embedding. An embedding is actually taking your space and you are seeing inside y some topological spaces. That's all. So you will be getting an equivalent copy of x underneath of y. That's what it says. Obviously, we can have a good proposition because you are working with a subspace topology, so we can restate it in the following manner. A function e from x to y is an embedding whenever it is a continuous one, whenever actually it's an if and only if condition, if and only if it is continuous, it is 1 to 1, And for every open set in Y in X, open set V in X, the image E of V can be written as W intersection Y, where W is an open set in Y. That is the proposition it says. So what it says actually, we have a function E from X to Y. X and Y are topological spaces. It is going to be an embedding. Embedding, what do you mean? This X is pushed inside underneath of Y. Whenever you are looking at X and E of X I mean the range of X, actually E of X means the range of E. You're looking at the image of X under E, that's all. So that is this part. This is this part, E of X part. Now whenever you are going from here, the copy of X is at E of X. Now it is going to be an embedding provided it is a continuous 1-1 map, and it is every open set in V here. You look for the image here, I mean E of V here. That should be an open set W intersecting with this fellow, Y. Right? See, it's very much clear, because how an open set in the subspace topology is given. See, we are just restricting the function should be, it is an embedding if and only if it is given. 1-1ness is given, continuity is also supplied. We need only openness for the remaining part, but openness you have to talk about according to the onto part. The onto part is guaranteed at E of X. E of X is sitting as enjoys as a subspace topology of Y. So every open set in E of X, how will you describe? Any open set here, you have to look at basically an open set in Y intersection with this W part. That is what you have to look at. So what happens is, just revoke your definition of subspace topology and embedding, you will get that. It guarantees E is additionally going to be an open map, nothing other than open set here is mapped onto an open set in the range. That's all. Open set in the range means according to the subspace topology. It's an open set in the parent intersecting with that. That's all. So you'll be getting this proposition directly. So these are all straightforward. So we'll wind up all these discussions with some more two important problems. One is the extension problem and another one is the lifting problem. Both are important in various branches of mathematics, not only in topology. So you might have been seen these kind of things even in analysis also. So just to look at what is an extension problem is. It says the following, we can state it in the following manner. Suppose X is a topological space. Now, if Y is a subspace of Y is a subspace of X, and we have the inclusion map, obviously. Then suppose we have a function on Y. I may take a set, some topology, and if I have a function f from Y to Z, so the natural question is that, can you extend this function to X? That is what the natural question is. Extend to Y, what is mean by an extension? That is, there exists a function capital F from X to Z, so that F restricted to Y is F. That is what it means. If you are restricting F towards Y, it should be simply F. That is what. This is what the meaning of an extension. So diagrammatically, you can write like this. Diagrammatically, this F is going to be a composition of F and I. Right? So whenever such a function F exists, we say that the function is an extension. See, extension in a general case, this extension problem is there. Not only with the topology also, just with sets you can play about that. Y is a subset of X. If you have a function f from Y to Z, can you extend it to a larger set? That can be obviously possible by just defining some evaluations. But we are dealing with topologies. So our concepts always take care of topological properties should be maintained. We mean continuity is the vehicle which carries from a topological space to another topological space. So we need continuity for the extensions. We already know that the inclusion map is always continuous. So given with a continuous function, what you are searching for is, will you get a continuous extension? That is what is important. Whether can you find an f from the parent x to z, or the larger space x to z, so that f dot I is giving f, which means can you extend continuously to x? That is more important. That is why extension problems are come. It's a very important problem you might have been already seen in analysis. Let me just point out it. See, suppose we are looking at 0, 1, the open 0, 1, open interval 0, 1. It has a topology, natural topology, space topology is there. So 0, 1 to R, if you have a function, a continuous function is given. So a natural question is, on the closed interval 0, 1, can you extend it? Which means, can you have a continuous extension? Continuously, can you extend it? So we have the inclusion again here. This is continuous, and when it can be extended continuously. A continuous function is given. How can you extend from 0, 1 open sets to the closed 0, 1? This is a fundamental problem in analysis. Then it definitely we know that you have to talk about something about uniform continuity and all. So just refresh your analysis days and try to answer whether the continuous extension exists or not. Once you are discussing the extension problem, dual problem also will come. How will your dual problem can be discussed here? All the arrows can be reversed and the concept will become easily. That's also equally important. I'll just state for that. In that case, what it happens is, suppose P and F are given. See, X and X, Y, they are all topological spaces, and that is also a space. If P is given from X to Y, and F is a given function from Z to Y, remember all they are topological spaces. So once again, the dual problem is nothing other than that, can you find a function f so that the following diagram commutes, which means f can be written as P dot f, capital F. Diagram commutes, it just means that. P dot f will give back f. So a continuous lifting is possible or not. That is a dual problem. So, but whenever you are talking about this commutativity of the diagram, remember that see the small f you are looking at, the range of f should be in the range of P. That is a theoretic requirement. But most of our lifting problems, P is going to be an onto function. Remember, whenever you are discussing all such things, you are interested on continuous fellows. P is a continuous function. F is also a continuous function. Then we are searching for a continuous lifting here. Whether such a continuous f is available here and all. There are many problems in analysis and complex analysis which are very much enjoying the lifting problem and all. So various exercises, one can see it from different branches of mathematics, and even topology is the basics for the things. So extension problem, lifting problem, and in general embedding problems and non-embedding problems, all are really making the subject more rich, and how to say more ways of doing the things with algebraic topology and all such things. We'll stop it for the time being.